Hi guys, day 2 of Riemann sums, and really just looking at some specifics dealing with limits of Riemann sums. Before we get started, I would love for you to hit pause and try this warm-up. What I want you to do is see which is the greatest, the left, the right, or the actual integral itself. So hit pause, try these 2 warm-up problems. Okay, hopefully you had a chance to look at these and maybe even use some of what we did yesterday with our notes. I should be able to determine, just by looking at whether it's increasing or decreasing, whether the left hand or the right hand is going to be an over or under estimate, meaning which one's going to be above the actual value and which one is going to be below. But let's say we didn't. We should be able to draw our rectangles. So if I look at my left-hand sum, for example, for this graph, my left-hand sum, no matter how big of rectangles I draw, are going to be just a bit more than the actual area. So I would say the left-hand sum is going to be the greatest. The actual area under the curve, so this is the actual area. And then that leaves by default my right-hand sum here. But that should make sense because my right hand connects there. It's just underneath the curve. Okay, so how does that look different? Well, let's start with my left hand again. If I start with my left hand, I have rectangles. And no matter how many I choose to do, if I do 4 rectangles, if I do 52 rectangles, each one of these rectangles is going to be just slightly below the actual value. So my left-hand sum would be here, and my actual value of the integral would be in the middle. And then by default, my right hand, even if I draw it in, would be here. How do we do? Okay. I want to review with you the summation notation. We haven't used it in this class just yet. Hopefully you have seen it in the past. If you were to see this expression, would you know what to do with it? Do you even know what it says? Hopefully you know this says the sum of the terms from 1 to 4 of I squared. Meaning what I want to do is plug in 1 to 4, 1 squared, 2 squared, 3 squared, 4 squared, and find the sum of all of those. So 1 plus 4, so we get 30. Hopefully you know that summation notation because we're going to use it a little bit today. Okay, one more warm-up problem. I would like you to find the area under this curve using the definite integral. All right, using the definite integral, we would have negative x cubed over 3 plus 2x squared, evaluated from 0 to 4. So using that fundamental theorem of calculus, oops, that wasn't supposed to be an equals. We would get, that would give us negative 64 over 3 plus 32 minus 0. So we would get 32 over 3. So approximately 10.667. Keep this number in mind. We're going to come back to this. There's just not room on this front page. So keep that number in mind. Okay, moving on. All right, what we want to do today is we want to convert a definite integral into a Riemann sum and look at what that actually looks like. So I know we already know the area under the curve. We got that the area under the curve was approximately 10.667. we said we were going to keep that in mind. Now, we know that when we're looking at area, especially of rectangles, we're looking at base times height, right? And we feel pretty good about that, but we need expressions for both. So let's start with the delta x term to figure out what our base might be. Remember yesterday we said that if we're going to find a delta x, to find our delta x, we take our ending point and our starting point and subtract them and divide by the number of rectangles. So in this instance, if we did 4 minus 0 over 4, we would divide 4 by 4 and our delta x would be 1. Or if we did 40 rectangles, I'm not going to ask you to draw 40 rectangles, you're welcome on that one, but we could, because we know that the more rectangles we draw, the more accurate we get. So we would do that would still be 4 minus 0 divided by 40, or 1/10. So my delta x is 1/10. And if we did 400, also not going to ask you to draw that, we would get the delta x was 1/100th. So that would be the width of each rectangle. It would be 1/100th of a unit wide. So what would that look like if we had the theoretical value of n? Well, delta x in this particular problem would be 4 minus 0 over n. So 4 over n. Now what would that actually look like generically? If we had to do that for any endpoint, well, we would take our endpoint and divide by the number of rectangles. Keep this in mind. We'll come back to this. But for our problem now, we'd have 4 over n. Okay, so let's now talk about the height of each rectangle. And we'll refer to the ith rectangle. Yeah, that's a thing. Only in math would we say ith. It sounds so weird. But we're talking about the I rectangle that's out. So we start at 1, 2, 3, 4, and we keep going until we get to some arbitrary rectangle that is the ith rectangle. Why they chose I don't know, but we choose I. But we want to write it in terms of n. So let's first think about the fact that if our delta x equals 4 over n, then the first x value that we come to is the starting value plus 4 over n. And then the next rectangle base that we start at would be the starting value plus 4 over n plus another 4 over n, which would be the starting value plus 2 times 4 over n. And the third rectangle then would be the starting value plus 3 times 4 over n. So if we get to the I rectangle, we are at 0 plus I, because we don't know how many I is, times 4 over n. Okay? If we look at this in terms of not this problem, but all problems, we may say that xi, the ith rectangle, is the starting value plus I times that delta x, because that's what that 4 over n is. So keep this in mind. We'll come back to it too. Okay, so let's find the height for our particular rectangle. Well, just so you can see the pattern, our first rectangle, which is f of x1, the height of it, well, we know we get the height by plugging in the x value. So we get the height by plugging in x1. Well, we know what x1 is. We know that x1 is 0 plus 4 over n plus 0 plus 4 over n. So there's my first term. So that would be the y value. That'd be the height of that rectangle. Well, I could keep going. And if I looked at my second rectangle, which would be f of x sub 2, plugging that in, I would get the opposite of, well, we said x sub 2 was 0 plus 2 times 4 over n. I think you can probably guess where this is going. So if I wanted to figure out the height of the ith rectangle, I would get it by plugging in x sub I into the equation that we already know. So if I plug in my I term to my equation, we get this. Now obviously this could be simplified. So let's look at what that looks like. I'm going to scroll up. It says, what's the area of each ith rectangle? Well, generically, we know area is base times height. Well, we just found the height and the base. We know for us, oops, let's go back to a pen. Area equals the base times the height. And for this particular triangle, the base that we said was 4 over n, that's an n, not an h, times, well, then we have this crazy thing here. So I'm going to simplify this. It would be negative, let's call this 4i over n squared plus 4 times 4i over n. So I have my base and my height would be an expression for the area, for the ith rectangle. Well, if I know the height of if I know the area of the ith rectangle, then I can find the area of all rectangles by doing the sum from I equals 1 to I equals n, the number of rectangles, and my area would be the base times the height. Now, often we see it written with the height first, just in this summation notation. It's not wrong to write it the other way, just so you know, you just will often see it this way. And this is the height. Now, this is of my right-hand rectangles. And the reason it's of my right-hand rectangles is because the height that we took starts when n is 1, not when n is 0, which would be my left rectangles. So this is the one we're going to use primarily, but we could go backwards and get the left-hand rectangles. It would look the same other than it would start at 0 and go to n minus 1. So it would go from 0 to 3, which makes sense if we're looking at the left-hand rectangles going from 0 to 3. There'll still be 4 of them. And then nothing else changes here. So this would be negative 4i over n squared plus 4. So that would look the same. It'd just be the starting and the ending value. Okay, so this is called the the sum of the area using a Riemann sum, just the notation of it. Okay, so let's look at how we can use our calculator to do this and what it actually looks like, because remember our whole goal is to get back to that 10.666667 number. So let's look at our calculator. Okay, so we are going to use our calculator, and I have a video showing you how to set up the calculator. But first we're going to look at it for several values of n. So let's look at what that looks like. Well, first off, I'm going to use n equals 4 because that makes the most sense. We did that up top, where delta x would be 1. Okay, and then I'm going to do what is that number? That was supposed to be a 1. And then I'm going to do that same one, n equals 40, where delta x is 0.1. And then I'm going to do n equals 400. Then delta x would be 0.01. But so let's look at what that looks like, what I'm actually typing in. When delta x is 1, it means that the value of the variable at that moment. Remember we said was that a plus I delta x. So in this case, what I'm looking at is my starting value of 0 plus I. I in this case references just x. So it would be, and my delta x would be 1. So it would be 1x. So 0 plus 1x is what I'm replacing for the variable in my function. So what I'm going to do in my calculator is I am going to start in y1, and I'm going to type in my equation, and then I'm going to show you how I'm going to let that variable be there and what I type in my calculator. So hopefully this will be okay. So if we look at the calculator, what I'm going to do is in my y1 type the equation, and then I'm going to hit math, and I'm going to scroll all the way down to number 0, which is summation. And in the summation, I'm going to tell it I'm going to go from 1 to 4. The number of rectangles that I'm typing in, that's my upper bound. And then I'm going to go and choose y1. And then I'm going to do parentheses 0 plus 1x. The reason I do that is I'm telling the calculator that I want 0 plus 1x to be my variable for y1. And then I'm going to multiply it by 1. Now, I'm going to go through and repeat this process for all of these. But what you're going to see is that my variable is going to change. So in this next one, my variable is going to be 0 plus 0.1x. And here my variable, my last one, is going to be 0 plus 0.01x. And you'll notice I'm multiplying by 0.1 because that becomes my height, or my width, sorry, my width and my height. So if we look at the calculator, and I'll write it down in just a second once I type this next one in. So x equals 1 to 400 of y1, so variables, y variables, function y1. And I'm going to tell it to be the variable of 0 plus 0.01x times 0.01, that width of the rectangle. Now you'll see this one takes a while to process, but see how it's still spinning up there, so I know it's still working. There we go. 10.6666. Notice how close I am to that value we said was the exact integral. So let's look at what we're typing in our calculator again, just so you can see it. So what I'm going to do is I'm going to put y1 into my calculator. Then I'm going to go to math, and I'm going to go down to number 0, which is summation. And what I'm telling my calculator to do is take the sum. Now in this case, I'm going to let it be x because that's the variable in my problem, from 1 to 4. Now this number right here is going to change based on the number of rectangles we're choosing. And then I'm going to put my equation in. This is the height, but I'm going to tell it to evaluate the height at the a plus ix, or the a plus the delta x I. Well, the I is x in this case, but this would be the delta x. So this number right here is my delta x. And then I'm going to multiply that by delta x. So that's what I'm telling my calculator to do. You'll notice on the next one that I typed in, oops, go back to pen, I did the summation from 1 to 40 the next time, 40 because of the upper bound. Then I told it to access the height, but use the variable 0 plus 0.1x. And 0.1 comes from the delta x. And then I'm going to multiply it by 0.1, which is my delta x. So remember, we're doing base times height. This right here is the height of my rectangle, and this is my base. So I've got my height and my base. We're telling your calculator, hey, take this height multiplied by this base for every number from 1 to 40 and find the sum of it, because that's adding up all those tiny rectangles that we can't do ourselves. Okay, let's put this in simpler notation. If I want to find the area under the curve using a Riemann sum, what I need to do is I need to take the sum from 1 to the number of rectangles of my function evaluated at a plus b minus a over n. That n kind of looks like a h. Let's rewrite that. Times I. Keep in mind that this expression right here is really equivalent to delta x. And I'm going to multiply it by that same delta x. The reason I'm doing that is because this portion right here is my height of each rectangle. This portion is my base of each rectangle. Now what I want to do to find a true Riemann sum is I want to take the limit of this as n approaches infinity. Meaning the more rectangles I can put in there, the more accurate my area is going to be based on the Riemann sums. What Riemann noticed is that if we do this over and over and over again, and we take the limit as n approaches infinity, we're actually doing the definite integral. And so he came up with the idea of that definite integral, or the way to notate the definite integral. All right, well, let's look at a couple of examples where we are going to convert the definite integral to a Riemann sum. So the first step that we want to do is we want to find our delta x. So we want to do our b minus a divided by n. So we'd get 7 minus 2 divided by the number of rectangles. Well, we don't know the number of rectangles because remember that's the limit to infinity. So then the height of these rectangles for each of them is going to be f of a plus delta x I. So in our particular problem, we would have the starting point would be 2. Delta x we said was 5 over ni squared plus 4. So you can see I just take and replace this variable with this crazy 2 plus 5 over ni. So then to rewrite this as a Riemann sum, this would be the limit as n approaches infinity of the sum of the numbers from 1 to n of the height of the rectangle, which we said was 2 plus 5 over ni squared plus 4, multiplied by the base of the rectangle, which is 5 over n. How'd you do? So try the next example and see if you can write it as a Riemann sum. All right, hopefully you had a chance to try this one. So you should have done delta x equals pi minus pi over 2 divided by n. So we have pi over 2 divided by n equals, let's make that a little bit prettier, pi over 2n. Then my height would be f of the starting point, pi over 2, plus pi over 2n I which means it would be sine, the height would be sine of pi over 2 plus pi over 2n I. So then the answer to this, write this as a Riemann sum, would be the limit as n approaches infinity. Oops. The sum of all the terms from 1 to n of the height, which is sine of pi over 2 plus pi over 2ni, times the width, which is pi over 2n. And there's the answer. How'd you do? Okay, so we have covered Riemann sums. We'll see them come up again just using approximation. But remember, the whole point of Riemann sums is it's a good way to find areas under curve if we're not given complete data. So that's what we would use this for. All right, you guys, have a good day.